Good morning. Uh, Welcome back. This is another lecture video. This is the last video, the last material that will be on the midterm exam. Today's topic is corrosion. Next week, I'll do 2 videos on material selection. I put it in between our 2 main units because it's not going to be testable. That being said, I would still encourage you to watch the videos. Hopefully the material selection methodology that I'm going to cover is interesting and helps to put a little bit of context and comparison between the materials classes that we've talked about in the first half of the quarter. And then Wednesday we'll have a Q&A session. If you don't feel like you need it or you want to take advantage of it, it's not mandatory, but it will be an opportunity to ask questions about anything you missed on the homework or anything that just isn't making sense. And then next Friday, there's no class due to the Memorial Day holiday. Neither is there going to be any class on Monday. And so the long weekend will be available for review and study. And then on Tuesday, not next Tuesday, but the following Tuesday, I'll be posting a midterm exam with instructions for you guys to self-administer. Okay. I'm going to go ahead and switch over. And these notes on corrosion are posted on Teams. Okay, this is chapter 17. So we've talked about so far the major classes of materials, metals, ceramics, and polymers, and also composites. And so we'll be covering corrosion processes or degradation processes for all of those classes of materials. As you'll see, the bulk of this material is about metals. When we think about corrosion, we are primarily thinking about metals, but as we'll see, polymers also have degradation mechanisms different, as you would expect, than metal corrosion, but still important. Okay, so when we say corrosion, what we're talking about, especially for metals, is a chemical reaction that results in either the dissolution, so the removal of metal atoms from the surface, or oxidation, where that metal atom is oxidized and forms an insoluble compound, oftentimes with oxygen on the surface there. Ceramics and polymers don't have this same oxidation or dissolution reaction. Ceramics, you can kind of consider it, I suppose, as sort of the product of a corrosive process. You know, if you recall, ceramics are ionic compounds, oftentimes including oxygen already. So you can think about ceramics as kind of being a post-corrosion, right? They're already essentially have been corroded. They already have the chemical reaction taken to completion, and then that byproduct is made into a material all on its own. And so since it's already been corroded, we don't really think about it as being susceptible to corrosion, which makes ceramic materials very useful for in high temperature oxidative environments. And that that's sort of that condition makes them corrosion resistant, since they've already essentially corroded. Polymers, we're not talking about corrosion in the sense, here we'll be talking about degradation, and we'll cover that a little bit more. So to jump into metals, what do we mean when we say metals corrode, right? Well, really what we're talking about is an electrochemical reaction that occurs on the surface. And so the electro part there refers to the fact that you have electron transfer and change in oxidation state of the metal atom. And so you have essentially two half reactions, we call oxidation and reduction each half reaction, that combine to produce, right, a chemical change. And a helpful mnemonic that I've always remembered from my chemistry undergrad is oil rig, right? So that's an acronym, and it stands for oxidation is loss, reduction is gain. And what it's referring to, losing or gaining, is the electrons, right? So this top reaction here, where we have kind of this M standing for really any metal atom, is being oxidized, right? Because it's going from a neutral species to an ion and giving up one or more electrons. And then here, the hydrogen is being reduced because it is gaining electrons to go from an ionized state to a molecule of hydrogen. And so you have, if you have an oxidation and reduction going on at the same time, right, you have electron transfer from the metal, or it was typically called the anode, right, to the cathode of the reaction. And oxidation and reduction reactions always happen in tandem. And just like we talked about with, say, ceramic materials, the charge is conserved. So if I'm producing electrons and they're not consumed somewhere else, then they'll just build up, I'll have a potential, and the reaction doesn't go anywhere. So you need both sides to have the reaction continue. And so since you have electron transfer, you also need to have a conductive path, right? So if there's no conductive path between, say, the metal that's being oxidized and the metal that's being reduced, say in a galvanic cell, we'll talk about later, then the reaction also doesn't continue because there's no path for the electrons to get to where they need to go. So you'll build up a potential on some part of the surface, and it'll just sit there. This in the sense of material science, usually we think about corrosion as being something to be avoided, as an unfortunate side effect of using a particular material, as a nuisance. But in batteries, for instance, this same reaction is put to good use, and the electron transfer becomes a current that we use to do work. In this sense here, say if you had a zinc anode, you could also combine that with, say, copper cathode. For instance, this is just the zinc hydrogen. This would say a chunk of zinc in an acid solution. But you see here that the zinc is ionized. Those electrons are given up to the hydrogen. And that's just an illustration, kind of a general dissolution mechanism. But you could also think about these electrons as flowing through an external circuit and ending up at a cathode, and then say plating metal from a solution onto that cathode. And as the zinc is consumed, right, this current is driven, and when it's gone, right, that's the end of the reaction, the end of the battery. That's what you mean when a primary battery goes dead. And in a rechargeable battery, you would have this would be reversible, but it's the same reaction in a battery that we're talking about on the surface for corrosion in many cases. Okay, so how do you know whether a reaction will occur, or how fast, or whether or not you should be worried about a particular material corroding? To answer this question, different reactions have been measured and ranked, and this gives rise to two series, the standard EMF series and the galvanic series, which is shown on the next page. And in this series, what we have are a number of electrode half reactions, right? And so we have ions and the corresponding number of electrons forming a neutral species, and the standard potential is listed there as well. And so what is so these half reactions, so these are all measured relative to the hydrogen standard half reaction. So that's it right here, right, where we have two hydrogen ions combining with two electrons to form hydrogen gas. And so that is defined as the 0 point. And if you take that hydrogen and you combine it, right, say in this fashion here with zinc, right, so the hydrogen reaction becomes one half of the reaction. And then the other half are these other reactions where you have right, a metal ion combining with electrons to form the metal, or you could reverse it and have the metal giving up electrons to join with the hydrogen atom to form the hydrogen molecule here. So you could make a cell out of hydrogen plus any of these half reactions, and that would essentially be a battery, and it would produce a potential. Right? There would be a force, meaning the tendency for electrons to either flow from the neutral metal, right, to the hydrogen atoms, to right, or vice versa, right? And so that gives rise to these negative or positive potentials, depending on which way the current is flowing when you combine these various half reactions. And so if you look at the, and these are all measured under standard temperature and pressure. So it's highly controlled conditions, but it kind of gives you a relative ranking of the electrochemical activity or tendencies of all of these different metals, which is a nice surrogate for their kind of corrosive potential. And if you notice here, they're ranked, and as a lower, higher on the chart, they have a positive standard electrode potential, which means that the equilibrium will tend towards taking, for this example here, gold ions and giving you gold metal. Whereas if you go to the other end of the spectrum here, you have a very negative potential, which means that this is actually going to drive the other way, and you're going to have a tendency for potassium metal to give up its electrons and form potassium ions. And since it's more negative, right, this is more strongly spontaneous in this direction. So if you look at the galvanic series, what you see is that elements that have a more negative standard electrode potential are more likely to be strong anodes and give up their electrons to form ions, and atoms that or elements that are closer to the top and have a higher positive standard electrode potential are more likely to be cathodes and to be inert, because they are more likely to scavenge electrons than they are to give them up. And so if you so as you go, right, you see you have some of your group 1 and 2 metals, right? So potassium, sodium, magnesium, aluminum, these are all group 1s, right? And if you think about the periodic table, right, it should make sense that these elements are likely to give up electrons, right? Recall, right, they have 1 or 2 s electrons, and if they give up those electrons, then they have a full valence shell just of the next lower electron shell. So the periodic table, right, would predict that these elements would be likely to give up electrons and become ions, right, because they have a full valence shell in doing so. Likewise, you come down here, you have your noble metals, right? You have platinum and silver and gold, all having positive standard electrode potentials, right? And so this helps to explain why you could be panning for gold, say in a mountain stream, and find a nugget of gold, right? You don't find like gold oxide. You find gold because it spontaneously forms the elemental gold um, uh, as opposed to say a gold ion. And this is useful in a corrosive sense because if you take any element here and combine it with or put it in contact with another metal that is far removed on this EMF series, right? You can expect that you will form a high standard potential in that cell, and it will lead to the relatively rapid dissolution into ions and then into solution of the anodic metal, right? So you combine right here this delta V is the combination of the standard potentials of each of the half reactions. It also means that that any metal that's further down the series is going to corrode before a metal that's higher up the series. Okay. And I mentioned it earlier, but I should note that the EMF series is produced under standard temperature and pressure, and also with 1 molar solutions. And if you change those conditions, then you change the potential also, right? And this is described by the Nernst equation, which is shown here. And under conditions under which the EMF table was generated, they are setting the temperature at, I believe, 25C. This is a standard temperature. And then they have 1 molar solutions of both of the metals in both the half reactions. And so you have the natural log of, well, this is 1 over 1, which I think will cancel this term out. And so the delta V that you have up here, right, is just the Nernst equation, but with the standard conditions that cancel out this second term. But if you're not under standard conditions, which practically you won't be, then you're going to modify the potential slightly depending upon how far off you are from those standard conditions, right? So we see here that we're going to have a higher potential as the temperature increases. We're also going to have a higher potential as the concentration of M1 increases, which I believe, yes, that would be the metal, the anode concentration, right? Which would make sense. As there's more anodes, we would be driving the reaction harder. Okay. And so the EMF series is helpful to a degree in that it gives us a relative ranking for various metals, but again, it's under standard temperature and pressure, under prescribed concentrations, and so on a practical standpoint, it may not be useful from, say, a material selection point of view. And so in addition to the EMF series, we also have the galvanic series, and this is not quantitative in the same way. It's not measured, say, relative to the hydrogen cell half reaction like the EMF series is, and it also isn't of pure elements. Instead, it's more of, and it also is done in a solution of salt water. And that was chosen because salt water tends to accelerate this corrosive reaction and is of particular interest to navies who have large metal objects that are in salt water continuously. And so the response from a corrosion standpoint of these metals to saltwater solutions is of intense interest. And of all the three, the three main services, the Air Force cares a lot about corrosion, but the Navy, and and the Army too, but the Navy is at the forefront of interest in corrosion control, just because of the um, the very aggressive environment they find themselves in. Anyway, so the galvanic series gives you the same relative ranking and the same scale here, where you move down, you become increasingly anodic. So it's similar to the EMF series, but we're looking at real alloys, and it's a relative ranking, right? So we see here, again, magnesium, zinc, aluminum, right? These are highly anodic, right? Especially magnesium and zinc. And as you go up, right, you have platinum and gold again as the most cathodic materials, and then in between, right, you have iron materials of industrial interest, right? Iron and steel, cast iron, stainless steels, copper, brasses, right? These are real alloys that you would choose potentially to make something out of. And both the EMF series and the galvanic series give us a sense of whether or not a material will be anodic or cathodic. It also gives us a sense for what the spontaneous reaction will be, but it doesn't tell us anything about the corrosion rate, right? And if we could potentially have a material that will technically corrode, right, that will spontaneously go from pure metal to an ion or an oxide, but it may happen so slowly in a practical sense, right, that we could still use the material and it would have a suitable lifetime because the corrosion rate is low, even though it will spontaneously corrode. And so this corrosion rate is captured by this expression here. This is the CPR, or the corrosion penetration rate. And this is a combination of weight loss, and I believe a kinetic parameter in K here, and then density, the surface area, and time. So we see here that as the density decreases and the area increases, that we're going to have less corrosion penetration, right? So when we talk about corrosion penetration, what we are talking about is essentially removal of material from the surface, right? So this is measured in, say, millimeters per year or something, where you have uniform corrosion across the surface that wears it away over time. And so we see here, obviously, if you have a certain amount of weight loss over a longer period of time, the rate is going to be lower. If you have weight loss over a larger, over a smaller area, then you're going to have a higher penetration rate. So you can think about it, this is kind of a low-tech way of thinking about it. You can also think about it in terms of current density, where if you're corroding faster, you're obviously going to have the reactions occurring faster, and part of that reaction is electron transfer through the material from the anode to the cathode, giving you a larger current density. And so, but if you have a direct path between the anode and the cathode, i.e. it's been short-circuited, right, there's a connection there, any electrons that are generated can flow freely, then your corrosion rate is going to be controlled by something else. That will change the measured potential that you would get under equilibrium, right? You're sort of, since the reaction is basically chasing after a new equilibrium, which gives you a different potential. And the faster they flow, the more that potential is going to be shifted. This is what we call overvoltage. And so we have this rate limiting. There's some rate limiting mechanism, right? That controls the corrosion rate, and there are two main regimes that we would consider. Um, One is activation polarization, the other is concentration polarization. And this brings into, let's see if I can zoom in. Here we go. This brings into account the mechanism of the corrosion. And what's going to limit it is whatever is the slowest step. And so in activation polarization, right, you could have in many reactions, and corrosion reactions no exception, you have various steps in the process, right? So for instance, you may have adsorption of a hydrogen ion at the surface, right? And then you would have electron transfer to that absorption, and then maybe you would have bonding with another hydrogen, and then a desorption from the surface. And so you could break down the corrosion reaction into those intermediate steps, and each of those steps is going to be characterized by some activation energy, right? So as you're going from one state to the next, right, there's usually some amount of energy that's required to for this sub-step to proceed forward. It could be, and if it's the case where one of those steps has a higher activation energy, meaning that it is more difficult to proceed through that step, then that will become the rate limiting step. And if that's the case, then you're in a regime that is called activation polarization. And so that's characterized, if you look at a graph here, of current density versus overvoltage, right? In regions where you have an increasing overvoltage, meaning increasing the current density, right, provides more energy for that activation, provides more energy to get over that activation energy barrier, then you're going to get, more voltage gives more energy to get over that activation energy barrier, which gives you higher current density. And the way this is going, so more negative, so you as you go more negative, this is a spontaneous corrosion reaction, so more negative is a higher potential, at least the magnitude of the potential is higher, and so that's driving more current, and because the overvoltage is giving you energy to overcome whatever activation energy barrier of this particular step of whatever reaction you're talking about is your rate limiting or your bottleneck. But it could be that none of those steps are your rate limiting, in the sense that you're instead limited by the ability of your ions to get to the surface in order for any of these corrosion process substeps to occur. In which case, it's the diffusion across some depletion region near the surface that is your limiting step. Basically, any ions that can get across this depletion region will proceed through the entire corrosion process of adsorption and electron transfer and reaction and desorption before, say, another one can come in and take its place. And so the reaction is sitting there waiting for atoms to diffuse to the surface, and it's not actually the surface reactions that are slower, right? You're going to essentially consume every ion that makes it to the surface, and you're just waiting for more ions to make it across. In that sense, changing the overvoltage doesn't give you an increase in current density. And so if you see this flat line here, that's indicative of a concentration polarization rate limiting step where you're limited by diffusion. Okay. And so you have rate limiting, so you have the spontaneous nature of your corrosion reaction. You also have the rate at which it proceeds, And the corrosion rate also has dependence on other factors in the environment. Oftentimes, you will have not a stagnant fluid, right? And so, um, we're talking about here having this depletion zone. This is sort of assuming that you have some sort of stagnant fluid there. Oftentimes, that is not the case. So you could have fluid flowing in a pipe. You could have waves hitting against a ship. You could have wind whipping against a surface. Any place where you have fluid velocity, right, you're also going to have erosion happening due to, right, the impact of that fluid, which can accelerate the corrosion environment because the erosion is exposing new metal surface, which can then be corroded. So this is a chemical reaction, and so you would expect that as the temperature increases, then the reactivity is going to increase, especially if you are in this activation polarization region, right? Because remember, oftentimes as we increase the temperature, right, we're providing more thermal energy to get over those activation energy barriers, and so temperature is generally going to increase corrosion rate. Also composition of the material. We saw in the EMF series and the galvanic series that different metals, right, occupy different positions here, and some of them are more anodic, which is typically characteristic of being more susceptible to corrosion. And in addition, cold work can increase corrosion. I think Callister uses the example of a nail and the fact that the point and the head of a nail, since it's deformed when it's being made, are areas where there is more cold work, and also areas where it will corrode first and more rapidly. And so this also provides, right? Remember, cold work. We talked about cold working and then recrystallization for materials when you try to reduce the grain size. And so we know that cold work stores energy in the crystal lattice, right? And if you're in a regime where you are, where you are in activation polarization, where you need energy from somewhere to get over some activation energy barrier to some rate limiting step, if you have cold work that's storing energy in the lattice itself, right, that's another source for that activation energy, and so that can increase the corrosion rate. Corrosion is also just a general term for lots of different scenarios, and because corrosion is so costly to an economic, from an economic standpoint, we have gotten very specific about certain types of corrosion. And Callister goes through them. I'll kind of summarize them here. The most common form of corrosion is uniform corrosion, right? So if you've ever seen, an old car that has that patina, say, on the hood or the body, that is, it just looks red, right? That's uniform corrosion, where you've got corrosion initiating randomly across the whole surface. And this is really what we're talking about when we say, like, before a couple of pages ago, we had that corrosion penetration rate, right? And so we've got uniform corrosion over the whole surface, and it's just essentially corroding it at some rate. And so, if you had a chunk of steel sitting out, right, the thickness may decrease over the whole surface at some rate. This is just, when you think rust, probably you're thinking of uniform corrosion. A lot of these other ones are more insidious, and because they target like key parts, key locations. The first here is galvanic, and so it's called galvanic because it is referring to the galvanic series or the EMF series, and what galvanic corrosion, is most focused on. Is when you have dissimilar metal contact. So that would be, say, you have steel in, like in plumbing. If you have a steel pipe that's in direct contact with a copper pipe, right? The copper is more cathodic, and so the steel will corrode preferentially. And this is to be avoided because essentially you're going to set up a battery um, at this location, which is going to corrode the anodic material rapidly at that interface. You can also have corrosion happening in a very localized area, which, as we saw with fatigue and crack initiation, can be bad, right? Because if I have corrosion in a very specific area, what does that become? Well, it becomes an initiation site for crack. And this would be things like crevice corrosion, where you would have, say, a narrow region, say between two metal plates, something like that, where the conditions are much different than you would have, say, on the surface, right? You can have a confined space where the oxygen concentration can be much different. You can have collection of ions, right? And so you kind of have an accelerated electrochemical cell in that crevice. This is similar would be pitting, which is like crevice corrosion, except you're not, say, in between two plates or in a confined area like that, but it would be on a horizontal surface where you would essentially create the same conditions, but say at one point on the surface that forms a pit, and then you have the same sort of concentration of corrosive species in that pit. There's also types of corrosion that are more specific to certain alloys. That would be intergranular corrosion, where you get preferential corrosion at the grain boundaries, which can be really bad because it essentially disintegrates the materials, right? If you corrode the grain boundaries, the material just kind of falls apart. You can also have selective leaching, which is when you have an alloy, right? But one type of element is more anodic than another. It could be preferentially removed during the corrosion. In any of these things, so we've talked about erosion already, and you can have one form of attack, you can have multiple forms of attack. If they're happening simultaneously, obviously that's a different scenario. It's going to accelerate the loss of material. So if you have erosion and corrosion happening at the same time, right, it's going to be accelerated because the erosion is removing the surface oxidation and exposing new metal, which is then further corroded. So even if you have, which we'll talk about, I think, on the next page, a passivating film, right? If you're in erosive conditions, you can be removing that passivating film, requiring it to be regenerated, which consumes more material. The same thing, corrosion that's happening at the tip of a crack, right? So if I have stress in the material already, then I'm going to be attacking chemically and also opening the crack with the applied stress, right? And so those two forces together accelerate the decay of the material. And then a bit more specific still is hydrogen embrittlement. This is, I guess, kind of at the crossroads between corrosion and fatigue or failure, but you have a reduction in ductility in this sense from hydrogen atoms that diffuse into the surface, right? So it's kind of both, because it's chemical attack from the outside, which sounds like corrosion, but it's also reduction in ductility, which leads to premature crack growth and failure, which is, so it's, like I said, it's at the crossroads there. Okay, so what environments are most corrosive, right? Well, you're probably aware of, let's say, if you have a car and you've lived in, say, somewhere else besides Ohio, you might notice that maybe your car's corroding a little bit faster, or here in Ohio, right, because in the wintertime they put salt down on the roads to help to melt ice. And so that changes the the environment with regards to corrosion. And this is also mentioned before, that the Navy cares an awful lot about corrosion because they are in a saltwater environment all the time. And so that salt water is going to increase the corrosion rate in most cases. But you can get corrosion even places where you have fresh water, albeit at a slower rate. And what you have is moisture, wet environments with dissolved oxygen provide that that aqueous environment for ion transfer to set up your electrochemical cell. And so if you want to prevent, so we talked about a little bit about how corrosion occurs, and so the keys to preventing corrosion are to disrupt one or more of the requirements for the reaction to proceed. The easiest way from a materials science standpoint is to pick a corrosive resistant material. Generally though, the more corrosion resistant a material is, the more alloying elements it has, the more heat treatments it has, which drive up the cost. And so generally, you don't pick the most corrosion resistant material because it would be much more expensive. And so it's a balance in most cases between the expected lifespan of your component, the corrosion resistance of that material, and then the cost of the material. So if you're stuck with a material that's not as corrosion resistant as you would ideally want, there are some other things you can do to make it more corrosion resistant. The first is to change the environment that it's in. One of which is to, say, design, the flow of a fluid to prevent erosion, or you could, instead of picking a material that won't corrode, you could, one other approach that works pretty well is to pick one that will form a passivating layer, which we'll talk about a little bit more, I think, on the next page. If you have a closed system, say, fluid that's circulating inside of a car radiator system or so on, you could have other chemicals in that fluid that's flowing that inhibit corrosion, right? So these could be, say, chemicals that scavenge oxygen, right, to change the corrosive nature of the fluid inside of the system. And there's design, moving on, there's design choices that you can make that have corrosion impacts. The first of which is to avoid creating a galvanic cell, meaning don't place dissimilar metals in direct contact because the anodic one will corrode rapidly. The other would be to avoid having unions that provide crevices where you can set up these little corrosion cells, and then also avoid standing water. So if you have a system that gets wet, make sure that you provide holes for drainage so that it can dry out. Probably the most common way of dealing with corrosion, or trying to at least limit its impact, is to paint things. I remember hearing a saying about the Navy. They said, if it moves, salute it. Meaning, I guess, officers. If it doesn't move, paint it, right? And so this probably was made kind of tongue in cheek, but has an element of truth in that any exposed metal is going to corrode. If you can paint that, then what you're doing is you are removing the environment, right? That saltwater environment or that moisture environment from having direct contact with your metal. Also, using a paint, a sealant, is typically a polymer material that is going to be insulating, right? And so not only are you removing the environment, but you could be disrupting the current path between one anodic and cathodic region. The problem though there with paints and sealants, if you've ever painted anything, you know that 90% of a good paint job is surface prep, right? So if you're going to get good um, adherence of your coating to your metal, you're going to have good surface prep um, and take care in applying that paint. Okay, the last one here, and one I think that is the coolest, is cathodic protection, right? So here you're taking a direct advantage of the EMF series and the galvanic series and intentionally integrating into your system um, an element that has more anodic potential than the object that you are trying to protect, right? So in this sense, here in this example in the upper right, we have a steel pipe, right? A pipeline or a water main, something like that. And to protect it from corroding, right, because it's going to be contact with groundwater and in a corrosive environment, if you provide a current path, say through this copper wire, to a chunk of magnesium, right? Ions can migrate through the groundwater in the soil, and I have set up and I've changed the nature of the corrosion reaction. Instead of having iron oxidize, right, I have magnesium oxidize and give up its electrons to the steel, which becomes the cathode, right? And so I am intentionally sacrificing this magnesium material to protect the steel pipe, right? And so everyone's, this can waste away, and every so often I come back and I replace it, right? All along I'm protecting the steel pipe that I care about. And this, so this is done here, on pipelines. I can actually do it without needing to consume the anode if I have a rectifier, right? So this anode is more of a passive way of doing it. The rectifier would be more of an active way, where I am influencing the electrochemical potential of the situation by applying a potential from the outside. It's also done not so much with a big chunk of material that's connected by a wire, but oftentimes by coating a more a material to be protected with the anodic material itself, right? So if you've ever heard of galvanized steel, right, what that means is that it has been hot dipped in molten zinc and has a coating of zinc on the steel, and so right, the zinc coating becomes the anode and gives up its electrons to protect the steel, right? And this especially works if you have damage to that surface, right? So you're going to have uniform corrosion on the galvanized steel. So if you ever see that like white chalky surface residue that can form, right, that's uniform corrosion of the zinc. Also, if you were to have a scratch, right, you're going to have that region become the cathode and have the electrons donated from the surrounding zinc. So it's self-protective. Okay, so that's something you can do from the outside. Moving on to passivity, I mentioned that you're, well, I'm running out of time. I mentioned that your choice of material and its corrosion resistance is important. And one of the reasons, so you could pick, say, a noble metal, but that doesn't make a whole lot of sense in a lot of scenarios for many different reasons. And if you pick a material that's considered to be corrosion resistant, oftentimes the reason it is corrosion resistant is because it forms what we call a passivating film on the surface, right? And so a passivating film is essentially surface rust. It's surface oxide, but the key difference here is that that oxide is highly adherent to the surface, meaning it sticks and stays and protects the surface, right? So that's what we mean when we say it passivates. So it initially corrodes, but then it stops once it has the surface oxide film. This is what makes stainless steel stainless, right? It has these oxides on the surface that form with the chromium and the molybdenum and the other alloying elements. Also, aluminum forms aluminum oxide on the surface, which is another passivating film. And the reason that it passivates is two reasons. Is that In order for it continue, so if for oxidation or corrosion to continue, as I grow the oxide film, right, I have oxygen at the surface, then I have the passivating film, and then I have the underlying metal. And if this oxide layer remains in place, as it gets thicker, the oxygen from the surface needs to diffuse farther and farther through this layer to reach the interface to continue to grow the oxide. And the thicker it gets, the slower this process becomes until, you know, it essentially stops. And so you need an oxide layer, and you also need one that doesn't remove. It is not easily removed. And predicting that is helped by a number called the Pilling-Bedworth ratio, right? And essentially what we're getting at with this Pilling-Bedworth ratio is this is calculated from the density of the metal in the oxide and the atomic weight of the metal in the oxide. And what we are measuring with this parameter is the degree of matching between the lattice constant in the crystal structure of the metal and the lattice constant in the crystal structure of the oxide. And so if the Pilling-Bedworth ratio is closer to 1, that is a better match between the metal and the oxide, right? And so if there's not as much of a mismatch between the atomic spacing of the metal and the oxide, you're more likely to have an interface that is tightly bonded. And so if we look at metals that we know to have passivating layers, and we look at the Pilling-Bedworth ratio, we see that it is somewhere between 1 and 2. And metals that we know from experience to be non-protective, right, have generally a Pilling-Bedworth ratio that is either greater than 2, meaning there's, right, the oxide atomic density, right, there's a big mismatch there, or it's much less than 1, right? So in either case, they don't match up very well, which means that the oxide tends to flake off. And when the oxide flakes off, that exposes new metal, which then reoxidizes. And so as this process continues, right, the metal is consumed at a much more rapid rate. Okay. Okay, I'm running. This is the last page. Where am I doing on time? No. I gotta speed up. Okay, and so the kinetics of this reaction, or the passivating reaction, is characterized by a couple of these expressions, right? So if we look at a linear kinetic expression, right? So this would be weight gain, meaning of oxide. So as I oxidize the surface, I'm putting oxygen into the surface, which produces a weight gain as a function of time. So if I have a linear relationship between weight gain and time, right, this is the scenario where I would have a non-optimal Pilling-Bedworth ratio. The oxide would flake off and re-expose the surface, right? So I'm continually re-exposing surface, which is continually corroding and oxidizing, and I have a linear growth rate. For a passivating film, right, which forms a tight, well-bonded oxide layer, I'm going to have either a parabolic or a logarithmic form to my weight gain, in which case what I see is rapid growth at the beginning as I have a thin layer that can have oxygen diffuse through it. But as I get a thicker layer, right, I see a rapid decrease in the rate of corrosion as that oxide layer becomes a barrier to diffusion of oxide to continue to oxidize the metal underlying the oxide layer. Okay. You'll notice I completely skipped over ceramic corrosion. It's because, like I said at the beginning, ceramics you can consider them to be like already corroded, and so they generally have really high, corrosion resistance due to the fact they've essentially already been corroded. Polymer degradation, you can throw out all of the electrochemical stuff. because we're not talking about an electrochemical reaction with polymer degradation. Here it's more physiochemical, right? So we have physical and chemical forces. And a lot of these should be familiar from when we talked about polymer structure. So we talked about permeabilities. This is the idea behind swelling. So you would have small molecules that can get in between chains and soften them. This is what happens when we add plasticizers. But depending on the environment, right, this might either soften our polymer or dissolve it completely. This becomes harder to do as we have longer chains that are more entangled. More cross-linking or crystallinity that increases the bonding nature between adjacent chains, or lower temperature, right? Solubilities always would typically decrease with lower temperature. The environment also oftentimes includes high-energy photons, right? This would be, say, for outdoor polymers that have outdoor exposure, especially UV or ozone. Anything that provides enough energy or reactivity to attack the bonds in a polymer chain, right? So I'm going to have attack of these bonds and break the bonds. So what I'm doing is I'm taking my polymer chains and essentially making shorter polymer chains, which typically discolor polymers. So if you see things, forming a chalky surface, or becoming more brittle, right? So you see, outdoor polymers starting to crack. That's due to accumulation of all of this environmental damage due to bond scission from ozone and UV. And so, similar to what we had the EMF series or the galvanic series for metals, for polymers, right? We have other useful, charts that rank our polymer systems with regard to these environmental forces, right? So you can have different polymers resist UV degradation to different degrees, also oxidation in ozone. You see here that some polymer systems can have great resistance to dilute acids, and so oftentimes storage containers for chemicals are in polymer containers because, right, they're unreactive to those acids, whereas a metal container would be quickly consumed. Okay. Yeah, and so when you're making your material selection, right, environmental degradation, either due to oxidation or dissolution, corrosion, or degradation of polymers is an important parameter. And I'm not going to, I'm already a bit over, so I'll go ahead and wrap that up. Thanks.